What the heck?
Tagon.
Once again, it is bonkers hot, man. This is... Holy crap, dude, it's sweltering. Okay. So, today we're going to do a really cool investigation of a...
Wacky Calc Wednesday!
Just a neat representation of the Riemann Zeta function that I've known about for a while, and luckily it's a finite representation. So it's an integral over a finite interval, which means you can plot it in Desmos. And because you can express it in a finite form, you can even plug in the, also, reppin' your shirt, Papa. It's a good shirt. You can plug in the functional equation for it, and you can get the negative axis for the Riemann Zeta function. And so when we're all said and done today, I'll put a thing up on the screen that shows that you can actually do that. And so you can play around with the zeta function in Desmos. It takes a while to load because it is sort of a complicated function, but it's finite. That's the important part. Or it's not an infinite sum or an improper integral. It's just a regular integral, a definite integral, that is. So let's get started. So we're going to sort of define a neat little function, do a particular type of integral over it. It's in fact called a Mellin transform. But we'll just sort of evaluate it and see what it gets us. So let's do it. Okay, so today we're going to find ourselves a really cool representation of the Riemann Zeta function. The answer is sort of, in a way, given away in the what the f is it called? The thumbnail of the video, but it's slightly different from actually how it turns out in the end. So let's just adjust the camera. Okay, so we're going to define a function. We're going to let, there we go, g of x be equal to this funky looking thing, x times the quantity 1 plus the floor of 1 over x, or x to the negative first power, minus 1. And we are going to consider a Mellin transform of a function is usually written like this. So if you do the Mellin transform of g, then this is by definition the integral from 0 to infinity of g of x times x to the s dx over x. That's one of the ways it's usually written, or x to the s minus 1. But we're going to be doing a particular type of Mellin transform of this function today because of the way that the function works. It's really only defined over certain intervals, and so the Mellin transform is sometimes cut from the integral from 0 to 1, and then the integral from 1 to 0, depending on the power structure, or the power structure as in like the degree of the thing that's being plugged into the Mellin transform. In this case, we're going to need to do the 0 to 1 integral, so we're going to consider the integral from 0 to 1 of g of x times x to the s minus 1 dx, where, you're probably not surprised to hear, where first of all, s is a member of the complex numbers. So this is not any complex number. We'll find out what complex numbers they actually have to be, given the result that we're going to get. But let's just take a look at what this is. So what we're going to want to do is we're going to want to utilize a trick that I used in that video response to Michael Penn, where we sort of utilized the floor function and its relationship to integrals, depending on the integral you take. So what we're going to actually do is we're going to rewrite this integral as an infinite sum, right? So we're going to start off at n equals 1 and go to infinity, and it's going to be all the integrals from 1 over n plus 1 to 1 over n. So let's see how this would work. So at n equals 1, we're going from 1/2 to 1. At n equals 2, we're going from 1/3 to 1/2, and then 1/4 to 1/3, and then 1/5 to 1/4. And so we're covering the entire interval from 0 to 1, but it's turned into an infinite sum of intervals which progressively get evaluated over smaller and smaller intervals. But it does, in the limit, traverse the entire interval from 0 to 1. But this is important because notice the floor function that we're using has 1 over x in it. And since our bounds of the integral are based on 1 over something, we can actually utilize the trick that we did in that response to Michael Penn and transform this into a continuous function, or not necessarily a continuous function, but something that's related to n as opposed to being a function of x, which will allow us to sort of remove it from the from the integral in that way. So we have x times 1 plus the floor of x to the negative 1 minus 1, and that's all times x to the s minus 1 dx, right? But now let's consider what I was saying. So the floor of x to the negative 1, since that's the same as 1 over x, just like when the floor of x was, we were able to sort of let it be one of the values of the bounds because it sort of rounded down to those, we can actually do the same thing here. So if we know that 1 over x is going to be strictly between 1 over n plus 1 and 1 over n, then we can reciprocate all three sides and we end up with sort of the opposite relationship. So we get that x is less than n plus 1 and greater than n, which means that if we're taking the floor of 1 over x and our integral is only going between 1 over n plus 1 and 1 over n, that means that this is going to round down to n, right? For all of these intervals from 1 over n plus 1 to 1 over n, then this floor of 1 over x is going to round down to n every time. And so that actually drastically simplifies our expression. So now we can sort of multiply this x to the 1s minus 1 into the two terms here, and we get the sum from n equals 1 to infinity of the integral from 1 over n plus 1 to 1 over n of x to the s times n plus 1 minus x to the s minus 1 dx. So now what we can do is, these are just powers of x, right? So we can just evaluate them. We can just take the antiderivative. And quite simply, we end up with, and I'm going to break this up into n times x to the s and 1 times x to the s. So we're going to get n, first of all, we're going to get the sum from n equals 1 to infinity, and the first term is going to be n times x to the s plus 1 divided by s plus 1. The next term is going to be x to the s plus 1 divided by s plus 1 minus x to the s divided by s. And that's how you integrate each of those terms, since they're just powers of x, and we're evaluating that using the fundamental theorem of calculus from 1 over n plus 1 to 1 over n. So all we have to do is plug in these bounds and take the difference of those two terms. So we're just going to do it term by term. So now all we have to do is simply plug in the bounds and take the difference via the fundamental theorem of calculus. So the first term, and I'll do all the simplifications after, so I'm going to factor out 1 over s plus 1, and then I'm going to plug in 1 over n there, so we're going to get the sum from n equals 1 to infinity of n divided by n to the s plus 1, because plugging in 1 over n is going to give n to the negative s minus 1, and then we can bring that down to the denominator and make the power positive. So we have n divided by n to the s plus 1, which means one of the powers of n's will cancel, and we'll just be left with 1 over n to the s, right? Because we'll have n divided by n to the s plus 1, one of them cancels. The next term, we're going to factor out 1 over s plus 1 again. And we don't have an n in the numerator, so we just plug in 1 over n, and we get the sum from n equals 1 to infinity, or from n equals 1 to infinity of n to the s plus 1. And the final term, we're going to factor out 1 over s, and we're going to get the sum from n equals 1 to infinity of 1 over n to the s, right? And those are the first three terms, but now I'm just going to write the next three terms down underneath them, and we're going to get minus 1 over s plus 1, right? This is all just using the fundamental theorem of calculus, times the sum from n equals 1 to infinity of n in the numerator divided by n plus 1 to the power of s plus 1, n plus 1 to the power of s plus 1, right? And then we're going to get minus 1 over s plus 1. This is all part of the same equal sign, right? So this is just one line and this is the next line of it, but it's all on the right side of the equation, times the sum from n equals 1 to infinity of 1 over n plus 1 to the power of s plus 1, right? And then we're going to get plus, because we have to subtract, so this minus gets turned positive, plus 1 over s times the sum from n equals 1 to infinity of 1 over n plus 1 to the power of s. Okay, so we have quite a few symbols going on here, and we can drastically simplify a lot of this quite easily. So let's see if there's anything that we can immediately cancel. It doesn't appear that there is, but we can do some nice manipulations and it'll all actually turn out just fine. So what we're going to do is recognize a couple things. This is the Riemann Zeta function, its original definition. So because we have a bunch of Riemann Zeta functions floating around, we actually realize that the real part of s sort of has to be bigger than 1. So even though it's a complex number, it turns out that s clearly, if we want to let this converge, it has to have a real part greater than 1, or else we're not going to be able to evaluate these things with any convergent, meaningful results. So this first part is going to be 1 over s plus 1 times zeta of s, right? This is the Riemann zeta function. So this is going to be zeta of s divided by s plus 1. That's the first term right there. And this is zeta of s plus 1 divided by s plus 1. So plus zeta of s plus 1 divided by s plus 1. And holy Christ, it's so hot. Minus 1 over s times zeta of s, right? And now this part we have to be a little bit clever. So what we're going to do is we're going to plug in n minus 1 for n, and that means we're going to get n minus 1 in the numerator, and we're just going to get n in the denominator. But that means this has to go up by 1, right? We can't just change the value of the running index without changing the value of the index themselves. So now what happens is these n's will cancel, and then we'll be left with minus 1 over n to the s plus 1, but both of them starting at 2. So the thing about this is we're going to get zeta of s minus zeta of s plus 1, but both of those things are going to be missing their first term, right? Because we're starting at 2 instead of 1. So we're going to get zeta of s minus 1 minus zeta of s plus 1 plus 1, because the negative is going to have a 1 added onto it to cancel that. And so what we actually end up with is minus 1 over s plus 1 times zeta of s minus zeta of s plus 1. And right, the minus 1 that we get from the positive zeta is going to cancel with the plus 1 that we get from the negative zeta, or that we don't have because we're starting at 2. And we actually have to do the same trick here. We have to plug in n minus 1, and then this starts at 2. And so we're going to get zeta of s plus 1 minus 1 times minus 1 over s plus 1. So we get minus 1 over s plus 1 times zeta of s plus 1 minus 1, and then the exact same argument here. So we plug in n minus 1, the index has to go up by 1, and now we have zeta of s minus 1 all times 1 over s. So we get plus 1 over s times zeta of s minus 1. So we finally, so I'll just delineate this. So this is switching it up, right? So this was the evaluation of the integral using the fundamental theorem of calculus. This is replacing all what we know to be equal to with like the Riemann zeta function. And now we're just going to cancel our terms, right? Clearly this cancels with this right here, right? Because we're going to get, oh no, that doesn't cancel. Crap. Sorry, that doesn't cancel, my bad. So this right here is going to cancel with this zeta of s plus 1 over negative s plus 1, right? And let's see, is there anything else that we can cancel? Sure, we're going to get zeta of s over s minus zeta of s over s. So this term is going to cancel with that right there. And anything else is going to cancel? Yes, we have zeta of s over s plus 1. That's going to cancel with minus zeta of s over s plus 1. And so all we're left with in the end is minus minus, so positive zeta of s plus 1 divided by s plus 1 minus 1 over s plus 1 over s plus 1, right? So we get minus 1 over s plus 1 over s plus 1. So as it turns out, I hope that's visible on the camera. I think that's just getting to the edge of the camera there. Yeah, right there. I hope that's visible. So what we've derived is that this funky finite integral using a floor function with 1 over x gives us a finite representation of the Riemann zeta function. So let's rewrite what we've just derived, and we'll sort of talk about it for a little bit. So this is what we've just been able to show, that given this funky looking function here, if we take this particular integral, we get this result here. Now, this is not what the Wikipedia article says. So we can actually simplify this a little bit. We do s plus 1, so we get, so we have to multiply the top and bottom of this by s plus 1 and the top and bottom of this by s. So we'll get minus s minus 1 plus s, so the s's will cancel, and we'll get minus 1 divided by s times s plus 1. Right? But this is not what the Wikipedia article says it will be equal to. The Wikipedia article says that it would be equal to zeta of s divided by s plus 1 minus 1 over s times s plus 1. And this is just simply wrong, which means Wikipedia is incorrect. This precise integral actually equals this. If you want to get the Riemann zeta function out of it, we actually have to plug in s minus 1. So what we really want is this. We want the integral from 0 to 1 of g of x times x to the s minus 2 dx. So really we're taking the Mellin transform of g of x divided by x. But the point is that we end up now, by plugging in s minus 1, we get zeta of s divided by s minus 1 over s times s minus 1. Very nice. And that means that if we multiply s on both sides and then add this term, we actually end up with a finite expression for the zeta function, which is really amazing. So we have, therefore, the zeta function, the Riemann zeta function of s, is precisely equal to this function times s, right? If we multiply s on both sides, it'll cancel here and it'll just go right there. So we get s times the integral from 0 to 1 of g of x, which again, g of x is this function here, x times the quantity 1 plus the floor of 1 over x, all minus 1, g of x times x to the s minus 2 dx. And then when we multiply by s, it cancels the s's here, so we'll just be left with minus 1 over s minus 1, so we have to add that to the other side, so we just do plus 1 over s minus 1. And if you plug this into Desmos, you do in fact get the Riemann zeta function. And if you plug this into Desmos, you do get the Riemann zeta function shifted over to the left by 1. So the Wikipedia page actually is incorrect. I'm not sure how one would edit that and get it approved, but if anyone would like to edit it, it does need to be edited, as well as the page for the Riemann zeta function and the page for angle expansions, because this function can be used to determine angle expansions, needs to be corrected because the same error is on both pages. And if you plug this in along with the beautiful, and again, this is for s with real part, so the real part of s is greater than 1, right? So it's strictly on this half plane of the complex plane. And if you then plug in also the functional equation, remember this is I've never proved this on my channel, but this is a well-known fact, that this Riemann zeta function, if you wanted to find the analytic continuation on the left half of the plane, you use 2 to the s times pi to the s minus 1 times sine of pi over 2 times s times the gamma function of 1 minus s times zeta of 1 minus s. So this is the functional equation of the Riemann zeta function. And plugging in values of s that are greater than 1 here will result in the zetas that are less than 0 over here, which is really nice. So using this finite representation of the zeta function and this functional equation of the zeta function, you can plot this. The Riemann zeta function, as it refers to the real number line in, on the real number line. The only part that I don't have is the interval from 0 to 1. And I'm not really sure what part of what analytic continuation of a finite kind of the Riemann zeta function that I can use to determine that part. I know we can use this formula to get that part. So we know that the Riemann zeta function is also equal to 1 over 1 minus 2 to the 1 minus s times this alternating version of the Riemann zeta function. That's not too hard to prove, right? And you can theoretically use that for the interval from 0 to 1 because this is convergent, though not absolutely convergent, but it requires infinite precision, right? This sum has to go to infinity, whereas this function is well defined, so is this integral from 0 to 1, so it's all finite. So this one you can't really use for any finite representations, but if there is a way to extend the Riemann zeta function to the interval from 0 to 1 in a finite way. That would be brilliant because that would sort of allow you to complete the graph. Unfortunately, when you plug this in, it only plots till just before 1, which means this functional equation will only plot till just before 0. So it's not all there, and it's not perfectly accurate, right? Plugging in -1 for the Riemann zeta function should give -1/12, and it's ever so slightly off from -1/12, but it's pretty much bang on, and all the negative integers do give 0, which is what they should. Because it's not a complex plane, we can't see any of the non-trivial zeros, of course, but it still is quite pretty to see it finally represented in Desmos in its almost full glory. So if anyone would like to investigate further how to better represent it on Desmos, or give me a finite way of extending to the branch between, or the interval between 0 and 1, that would just be perfect. So thank you for watching this episode of Wacky Calc Wednesdays. I really hope this was an interesting foray into beautiful representations of the Riemann zeta function. And next up is the Bernoulli numbers and the Euler summation formula. So get ready for that, people. It's going to be good. Thank you very much for watching, and I'll see you next time.